And my name is Emma Frank, your regular tutor on mathematics. And now in this package, we are going to look at multiple integral. And it is assumed that the students are familiar with elementary calculus, so that they will flow in our study here of multiple integral. Now I'm talking about elementary calculus. I'm referring to integration of functions of one variable, because if you know integration of function of one variable, then it will be very, very easy to perform multiple integral. So let's look at it. Now we recall from integration of functions of one variable, that integral from b to a of f of x, the x, is defined to be the limit as n approaches infinity, and then change in x approaches 0 of f of x1, the x1, plus f of x2, the x2, plus we have plus f of xn, the xn. This is how we define it. Now we can extend this to functions of two variables, where we have the double integral. So we'll start with the double integral. Double integral. Now let R be a region in the x, y plane, in the x, y plane, in the x, y, in the x, y plane. Let R be a region in the x, y plane, bounded and let f of xy be a function of two variables x and y. Then integral, the double integral over R of f of xy, the R, will also be defined as the limit as n approaches infinity, and then we have that the R approaches 0 of f of x1 y1, the R1, plus f of x2 y2, the R2, plus f of x3 y3, the R3, plus f of xn yn, the Rn, where f of xi and yi are okay, is the subdivision subdivision of the area R, the region, that region R is subdivided. Method of evaluating double integral there are two ways of evaluating double integral, in which either ways yield the same result. So we have two approaches. So we say that either way yield the same result. Now let's look at the first approach. We look at the first approach, and then I want to make the definition. Let R be a region on the XY plane bounded by the lines x is equal a, x is equal a, y, yes, x is equal a, x is equal b, right? And the curve y is equal phi 1 of x and y is equal phi 2 of x. Continuous. These curves are continuous. Continuous in the interval. Now the interval is a less than equal x and less than equal b. This line, this line. Now let me show you the diagram so that we will imagine what we are trying to say here. Fine. I said let R be a region on the xy plane. This is xy plane, and then R is bounded by the lines x is equal a. So on the x-axis I have x is equal a, and there is a line at x equal a. I also have x is equal b, another line at x is equal b. It is bounded by this line, and cos y is equal phi 1 of x. So I have a curve like this. This is phi 1 of x, it's a curve. And then I have another one. This is phi 2 of x. So this is the region R we are talking about. Let R be a region. So this is where we are talking. Let R be a region bounded by this line and the curve. Now this curve is a function, and on this curve, what we see is that, okay, let this be phi 1 of x and this is phi 2 of x. So what it means is that phi 1 of x is less than equal phi 2 of x. This curve now. Less than this. But this is the region we are talking about. Let R be this region. Then, for us to get this region, the double integral over R of f of sy of f of sy dy dx will be equal integral b all over a and then integral phi 2 of x, phi 1 of x. Then we have f of xy dy dx. Now what we are saying is that the region R is equal to taking the integral from b to x in this axis, and then you also take from phi 2 of x to phi 1 of x. So we'll look at the example. Now we are looking at this example. We are going to evaluate the double integral over R of x minus y dy dx, where R is the region bounded by x is equal 0 and x is equal 1, and y is equal x, y is equal x squared. Now, from this diagram, we just drawn, we see that what they are saying in that question is that this line here corresponds to x is equal 0. Then this one is x is equal 1, just like that. And then we have a function. The function is y is equal x. Of course, y is equal x is a straight line like this, which we know, which is the identity function. And then another one is y is equal x squared. So this is the region we want to consider. Okay, so we will take the solution, and then we have integral, the double integral over R of x minus y dy dx. For our definition, will be equal to the double integral from 1 to 0, then double integral from x squared to x of x minus y dy dx. That is how we define double integral. The region now will correspond to this. Now, let us start that this will be the same as the double integral of 1 to 0. Then we'll first of all integrate with respect to y here. Then we have x minus y dy, then the x. And you see, the x is out. We want to deal with y first. We just one after the other, like we normally do, even in elementary calculus. We have that this will be the same as we have the same as 1 to 0. Now, if we integrate this with respect to y, we'll have xy minus y squared over 2. Yes, minus y squared over 2. The x, then we can now put the limit. We have x squared and we have x. So if we do that, and this will give us integral from 1 to 0. Now, if you put x squared in the place of y, then we have x squared minus x squared over 2. That is what we have. The x, of course, this will give us integral from 1 to 0, and we have x cubed minus x raised to the power 4 over 2. That is this side. Minus, of course, to minus the down limits, exactly what we normally do in the numerical calculus. So we are putting the upper one. Now, after putting the upper one here minus the lower one, so if you put it here, the lower is x squared, because we put x here, so give us x squared minus, we put x again here, we also have x squared over 2. Now, all over we have that this is the x. Don't forget about the x. Now this one tries to define the inside of what we are doing. So that we have integral from 1 to 0 of x cubed minus x raised to the power 4 over 2 minus x squared plus x squared over 2. That is what we have, the x. But I don't know the corresponding terms here. Let me make the corresponding terms to come out. That we have x cubed minus x raised to the power 4 over 2. Then here is 2x. We have 2x minus 2x minus x squared over 2. That's what we have. Minus 2x squared plus x squared over 2, the x. And that will give us, you see, this will give us, you see, minus this plus this will have, now this is integral from 1 to 0 of x cubed minus x raised to the power 4 over 2 minus x squared over 2, the x. So we now integrate with respect to x. Now integrate it with respect to x. So we integrate this, we have that this is x raised to the power 4 over 4. You know, we integrate here. We have 4 over 4. So integrating here, we have minus x raised to the power 5 over 10, because 5 times 2 it was 10, minus x raised to the power 3 over 6. So we can now put the limit, the upper and the lower limit, which is we have 1 all over 4 minus 1 over 10 minus 1 over 6. Now what is the LCM here? The LCM becomes 60. And then if you go here, 60 divided by 4 is 15. We have 15 minus 6. So 60 divided by 10 is 6. Then minus 10. So we then have minus 16 plus 15, which is minus 1 over 60. So that is the region R. That is the region that R occupies. It is minus 1 all over 60. If it is in meter, you say yeah, meter square. That is the area of that place that R occupies. We are looking at another example. I'm going to find the double integral over R of x, y minus 2x cubed divided x, where R is the region bounded by the curve y is equal to x and y is equal to x squared. So we'll take the solution. We have a double integral over R, and we have the function y is equal to x cubed dy dx. Now, what we will need now is, in this case, the limit of x is not given, so it is only the curve. But let's imagine the diagram that we just finished drawing. You see that the function, now this function is that upper function, the curve. And then this one is the down one. So for us to find the line x is equal A and x is equal B, we have to equate this and solve it simultaneously so we can get the limit of x. It's very, very simple. Now, if we do that, we will equate to get this limit, is to get the limit of x. We equate y is equal to x and y is equal to x squared. That is, we will have that x squared is equal to x, which means x squared minus 2x equals 0. So x will equal, now this x we have x minus 2 equals 0, meaning that x is equal 0 or x is equal to. So those are the points of x. We have got it now. So that the double integral over r of xy minus 2 x cubed dy dx now become integral from 2 to 0 of the x side, and then integral from x squared to 2x, from x squared to 2x for the y side. Then we have xy minus 2x cubed, then we have dy dx. So we are able to transform it. Now then we can now solve this to be integral from 2 to 0 of x squared and 2x. Then we have xy minus 2x cubed dy, then the x. You know what we are doing there, we'll first integrate this inside, and then when we do that, we'll have that integral from 2 to 0. If you integrate this with respect to y, you have x y squared over 2 minus 2x cubed y. I integrate it with respect to y, and that will give that is, we have finished that, and then we'll have our limit. We'll put the limit now, which is x squared, and when we also have what 2x dx. So when we put the limit in here, we will have that integral from 2 to 0, and then we have x squared over 2, because we are putting this first limit anywhere y is. So we have 2x cubed, then we have x squared, look at that, in the place of y, minus the down limit, which is x, then putting there, we have 2x, is it 2x here, squared over 2 minus 2 x cubed, then we'll put 2x in the place of y. Now don't forget that all these things we are integrating with y, so we substitute the limits, the upper and the limit, lower limit of y. So this will give us integral from 2 to 0, which is for x axis. Then this one, you know, this square will be x raised to the power 5 over 2. That is where this one will be. Minus, to multiply this, you have minus 2x raised to the power 5. Now, this side will give us minus, this one will be 4. Yes, minus 4x cubed. Minus 4x cubed over 2, you know, 2 squared is 4, so x squared is squared. So 4x squared times x is 4x cubed over 2, though this can cancel, but let's leave it first. Then if we go here, we have plus, you know, this one can affect. So we have plus 4x raised to the power 4. Then we have what? The x. Then this one can give us integral from 2 to 0. And then when we look at this term here, we have x raised to the power 5 minus 4x raised to the power 5 over 2. I'm taking LCM of this because they have the same power. Minus 2x cubed plus 4x raised to the power 4. And then I have the x, which is the same as integral from 2 to 0. And then I have, here will give me minus 3x raised to the power 5 over 2 minus 2x cubed plus 4x raised to the power 4. Yes, the x. Okay, so I can now integrate it with respect to x, and that will give me, if we integrate this with respect to x, we have minus 3 x raised to the power 6, you know, x plus 1, then over 12 minus 2x raised to the power 4 over 4 plus 4x raised to the power 5 over 5. Okay. Now, we'll not forget to put the limit. And this will finally give us, if we put 2 here, we have minus 3, 2 raised to the power 6. Okay, now what this gives us? Definitely, this will give us x raised to the power 6 over 4. Yeah, so let's simplify it at once and call it minus 2 raised to the power 6 over 4, because 3 can cancel here. Then this can also cancel. We have minus 2 raised to the power 4 over 2 plus 5, 2 raised to the power 5 over 5. So we have put the upper one minus the lower one. Of course, the lower one, everything will be 0 here. So we can now calculate the real value of it. So we know that 2 raised to the power 6, you know, 2 raised to the power 6, I think it's 64. Yeah, we have minus 64 over 4 minus 2 raised to the power 4 is 16. Okay, so we have 16 over 2 plus 2 raised to the power 5 is 32. Yes, so 32 times 4, 32 times 4 give us 128, okay, over 5. Now 64 divided by 4 giving us minus 16 minus 8 plus 128 over 5. So we find out that with this this is over 5 because of the simplification of this. That this is the same as minus 24 plus 128 over 5. Now the LCM is 5. Now 5 times 24, 5 times 24 will give us minus 120 plus 128 over 5, which is 8. Yes, which is 8 over 5. So that is the area that we are looking for, the region R, and it's 8 over 5. Now we want to look at the second approach, and we say let R be a region on the x, y plane bounded by the line, bounded by the lines, and the line C, y is equal C, and y is equal D. And the function x is equal, find one of y, x is equal phi 2 of y. These functions are also continuous in the interval c less than equal y and less than equal d. Then the double integral over r of f of xy, the x, the y, will be equal to integral of d to c, and then integral also from phi 2 of y to phi 1 of y. Then we have f of xy, the x, the y. And look at that. If you look at this one, what we are doing here is the limit here, which is constant values. Bring it up. Then the function is also first integrated with respect to y. You see, it's y that we are defining now. These two functions. Now let's see the diagram. I think the diagram will really help us to understand what we are talking there. Now in this case, the other one, the former one that we did, the line was here, x is equal a, x is equal y, the function, that is the curve in this way. But in this one, we have line here, yes, and this is d. We have another line here, which is c. Then we have curve, and this curve is continuous in this interval. That's what we are saying. It's continuous. It doesn't cut in the interval. That's what this thing is saying. It's continuous here. And then as it's continuous, it corresponds to x is equal phi 1 of y. This is the function. And then in this way again, we have another function, another curve. This is the function also. We have x is equal phi 2 of y. Now see the region that we are talking about. This region R, bounded by this curve, by these lines and the curve. See the region. The region R. So we want to integrate. We want to find this region. What is the region? What is the area of this region? So if you want to get the area of this region, it is the same as taking the integral from d to c, as here to here, and the integral from this way, which is this curve, from this curve to this curve. So that is what we are saying, and then we are going to take example of it so that we understand how to apply it. We are taking this example. We are asked to evaluate the double integral over R of xy, the x dy, where R is the region bounded by x-axis, the line y is equal to x, and the parabola x squared is equal to 4ay. Right, so now we will pick the solution. We have double integral over R of xy, the x, the y. Now first, we'll find the limits. You know what we are giving here? We are not giving the limits, so we have to find the limits ourselves. And how do we find the limits? First thing we'll do there is we have seen y is equal to x. Now let's also find y from here. We see that y is equal to x. Now from here we have x squared is equal to 4ay, which implies that y is equal to x squared over 4a. So that is the limit for y. Then for x, we can equate these values and solve for x, which we have already known. So that means 2x will be equal to x squared over 4a. And then that would imply that x squared is equal to 8ax. That's what x squared means. What we need is really x. So, which also implies that we can write like this, that 8ax minus x squared equals 0, meaning that x, we have 8a minus x equals 0. Now this time this, you can get back here. And this time this, you get back at x squared. So that means x is equal 0. And then x is equal 8a. Those are the limits for for x. Now, it means that integral, the double integral over r of xy, the x dy, will now be equal double integral from 8a to 0, 8a to 0, and the double integral of we have x squared over 4a, which is this y, to 2x. Yes, to 2x. X squared by 4a to 2x of x, y. Then we have the y, the x. Now, let's integrate with respect to y first. Then we'll have integral x squared over 4a to 2x, which is this. And then we also have x, y, dy, x. So we have integral 8a to 0. Now here, if we integrate this with respect to y, we'll have x, y squared over 2. So we'll now put the limit, which is x squared over 4a to 2x, the x. Then if we do that, we'll have integral 8a to 0. Now if I put this to here, we'll have x, then we have x squared over 4a in the place of y squared over 2 minus, this is the upper limit, so we minus the lower limit, which is x, then we have 2x squared over 2, the x. So, and that will give us integral 8a to 0. Where we also have this because x raised to power 5. Now if we go down, we'll have over 8 a squared over 2. That is what this place gives. Minus, going this way, we have 4x cubed over 2, the x. And that means what we have is integral 8a over 0. Now this place, we can write this place. You can write this place as 16. That's what I see here. 16 over a squared. That is x raised to the power 5 over 16 a squared. Okay. Already here is 16. Okay. This is 16 a squared. So here we have 16. 16 a squared, because this square gives us 16. Okay, this time this square is 4, and this x raised to the power 5. So this square gives us, alright. So if you times this, we'll have 32. We'll have 32 x squared minus 2x cubed. Minus 2x cubed. Okay. Minus 2x cubed. So, and then we have the x, can now integrate it with respect to x. But I know that this is the same as integral 8a, now this is a, to 0 of x raised to the power 5 over 32a squared minus integral 8a to 0 of 2x cubed. We are integrating the x minus also the x to respect to x. I try to bring out this constant so that it will be easier for us. So we have 1 over 32 a squared, because this is constant a. Then we have integral 8a, then we have x raised to the power 5 dx minus 2 integral 8a to 0 of x cubed dx. Now if we do that, we will have 1 over 32 a squared. If you integrate this, you will have x raised to the power 6 over 6. Then we have 8a to 0 minus 2. Then here will be x raised to the power 4 over 4. Then we have 8a to 0. So this place now become 1 over 32 a squared. Then if you put 8a here, we have 8a raised to the power 6 over 6. Of course, we take the limit of the lower one, it will be 0. Minus, if we go this way, we have 2, then we have 8a raised to the power 4 over 4. So if we take the limit, also will be 0. Now see, everything now is in constant form. So everything becomes constant. We have the constant now. Now, this is the same as 8 raised to the power 6, a raised to the power 6. Now, let me check that. 8 raised to the power 6. Okay, we have 262.144. And then if we have that, we have 262.144 a raised to the power 6. Now this side, you can times this side, that is 32. 32 times 6, giving us over what? 192 a squared minus 8 raised to the power 4. 8 raised to the power 4. It was 4, okay, times 2. Let me put it in 2. We have 8,192 a raised to the power 4 divided by 4. So now this is how it is. If we can evaluate this now, then we get a particular answer. That is dividing this by this. Okay, let's finish it up. 262.144 divided by 192 become 136533. Now this can cancel this. We have a raised to the power 4 minus, we have 8192 divided by 4 give us 2048. Then you have a raised to the power 4. So this minus this can now give us a very single value. So that is what we get. So we have 1365 minus 2048. We have minus 683 a raised to the power 4. So that is how we can evaluate it. Alright, so the next one we want to look at is triple integral. So let's just make some introductions that in the same way the double integral is viewed as the area of the region R in the xy plane. That one is the xy plane. in the xy plane, the triple integral can also be viewed as the volume. You see, the triple integral can also be viewed as the volume of a region V in the three-dimensional plane. Dimensional plane. Of course, we know three-dimensional plane. So that we have the triple integral over V of the Z, the Y, the X. So we'll have like this, and we call it triple integral. Now, we are going to pick. So we look at the example. Says we should evaluate the triple integral, this triple integral over V, where V is the region bounded by X, that is minus V is less than X and less than 7, and 0 is less than 1 and less than 2X. Y is less than equal Z and less than equal X minus 1. No, minus 3 is less than equal X and less than equal 7. Same thing happens to Y. 0 is less than equal Y and less than equal 2X. Now, we'll pick the solution. Double the triple integral over V of the Z, the Y, the X will be equal. We look for X here is 7 to minus 3. Then we have another one. Here we have 2x to 0. Then we also have for z, here we have x minus 1 to y. Then we have the z, the y, the x. So we have translated it because they have told us the area that is bounded by this region that we want to compute the volume. And so this will be the same as integral from 7 to minus 3. 2x. So we are just taking them one after the other. That is the difference for triple integral. Then we have this x minus 1 to y. Then if we integrate that with the z, that is the first integration there. And then we let the y, the x out first and deal with this. So that will give us 7 to minus 3, 2x to 0. And then if we integrate this, we'll have z. So we now put the upper limit, which is x minus 1. Then we have y. So we have the y, the x. Now if we do that, we have integral from 7 to minus 3. Then integral from 2x to 0. Then we have x minus 1 minus y. You know how x minus 1 is the upper limit minus y. And then we have the y, and then we also have the x. So if you do that, this is the same as 7 to minus 3. And then we now integrate with respect to y. So we have x minus y minus 1, to write it this way. The y, that is what we are integrating with respect to. So the x, we keep the x outside. Then when we integrate this with respect to y, we will have integral from 7 to minus 3. Then we have x, y, we are integrating with respect to y, minus y squared over 2 minus 1. Yes. Then the limit is 2x to 0. The x. So if we do that, can now substitute the limits. And we do substitute it. We have from 7 to minus 3 for x, and then we have x, then we have 2x in the place of y minus 2x squared over 2 minus 2x. Then the downside will be 0. You know, we're supposed to put the upper and the lower, so we know the downside will be 0. So the x, now this will give us integral from 7 to minus 3. Then if you do this, you have 2x squared minus 4x squared over 2 minus 2x, the x. Now what we have there, this is minus 2x squared plus 2x squared. So at that point, no, you see, if we take the essence of this, yeah, we'll have integral from 7 to minus 3. We have 4x squared minus, is it 4x squared minus 4x squared, okay, 4x squared minus 4x squared, because this will be 4x squared minus 4x squared, so that will be 0. 4x squared over 2 minus 2x, the x, and so that will give us integral from 7 to minus 3 of minus 2x, the x. And if we integrate this, we will have minus 2. We like to put that over 2 because this side also cancel. So we have this over 2, so they will cancel themselves. And so what remains is minus x squared. Then if we put the limit from 7 to minus 3, we will have minus 7 squared minus, I said for the lower, we have minus 3 squared, and that will give us minus 49. You know, 7 squared is 49 minus, now look at this, we have minus 9. Yes, because this is 9, so this 1 minus 9. But if we use this to multiply this, then it will be equal minus 49 plus 9, which is equal minus 40. So minus 40 becomes the volume of the region that we are considering. Okay, so if it is in terms of meter, then we have minus 40 meter cube. We have it in cube because we are talking about the volume. So this is how we can compute the triple integral, taking one after the other. Right. The next one we are looking at, the next topic is the line integral. Now let's see be a curve. On the xy plane that connects two points A and B. That is, what we are trying to say is this. We have the xy plane, and then we have curve like this. On the xy plane is the curve. We have a point A, A1, B1. We have another point B. We have A2, B2. Is a curve. Now, length U of xy and V of xy be two functions of x and y respectively. respectively, whose partial derivative exists and continuous everywhere or at every point, and continuous at every point on C. Now you know this is C. This curve we're talking about, and everywhere on C. Then integral over C of u of x, y, dx plus v of x, y, dy is called the line integral. It's called the line integral along the curve C. Along the curve C. So this is the line integral. Now we will take example and see how we evaluate the line integral. It's so interesting and very simple to deal with. Now we look at this example. We are asked to evaluate integral over C x square y dx plus x square minus y square dy from 0, 0, that is from the origin to the point where x is 1 and y is 4. Along the curve is y is equal 4x squared. Okay, so we'll pick the solution. Now integral over C x square y dx plus x square minus y square dy is what we have. Now we are given that y is equal 4x squared, which means dy dx is 8x. See, dy dx is 8x. So we now have that, it implies that dy is equal 8x dx. So when we do that, we now substitute the value of y. See how this line integral work. We put the value of y. Anywhere we see y, put the value of y. Then when we go to dy, we put the value of dy. So we see everything will turn to the variable x. Then we now integrate. It's very simple. So now what we'll do is, this will be the same as writing integral over c of x squared. Then y is 4. So we have 4x squared. Y is 4x squared. So we are putting that in this place. In this place of y. Dx plus x squared minus y squared. So we have 4x squared. That is how that one look like. Then the y is 8x dx. And that will give us integral over c. Now this one will be 4 x raised to the power 4 dx plus, you see this place need attention because this place is the same as writing x squared minus 16x raised to the power 4. Then we have 8x dx. So, and that will give us integral over c. We have 4x raised to the power 4 dx plus. Now this time this will give us 8x cubed because there is x here, so we have x cubed minus 16 times 8. Okay, so 16 times 8 giving us 128. So we have minus 128x raised to the power 5 dx. So that means integral, we can now write it this way, that integral, we are integrating from the origin, to point 1 and 4. So integral from 1 to 0, I can see now, because we are giving it the limit now, of 4x raised to the power 4 plus 8x cubed minus 128 x raised to the power 5 dx. You see, I am just factoring out the x because I am able to change everything now to the x. So I will now start my normal integration, which means what I have here will be 4x raised to the power 5 over 5 plus 8, 8 x raised to the power 4 over 4. So it will give me 2x raised to the power 4 because there is over 4 here now. And then this will be what? Minus 126 x raised to the power 6, okay, minus 128 x raised to the power 6 because of integration over 6. Then we pick the limit, which is 1 to 0, and that will give us 4 1 over 5 plus 2 1 raised to the power 4 minus 128 1 raised to the power 6 over 6. So this becomes 4 over 5 plus 2 minus 128 over 6. Now if we do that, and if we do this, we will have, now let's pick this. This will be the same as 14 over 5 minus 128 over 6. I'm taking LCM of this to now. Yes, because this will be 10 times 2. So we have this. Now, which is the same as 30, because the LCM of this is 30. 30 divided by this is 6. So 6 times 14. 14 times 6 give us 84 minus, if you go this way, you will have 128 times 5, and that is minus 640. So minus 640 plus 84 can give us minus 556 over 30. So that is the line integral. That is how we do it. It's very, very simple and short to do. Alright. So the next example on line integral, we are going to evaluate the line integral over a closed curve. Now look at this one. You see this symbol now. It's different from the other C. So this one tells you that what we are integrating around a closed curve. Right now, a closed region, a closed figure. Okay. Now, x squared, the x plus 1 plus 2xy dy around a triangle. So the figure now that we are integrating is the triangle in the xy plane with vertices at A, that is the origin, then B is 2 and 0, and then we have T is 2 and 4. You see, so this one has similar approach to the other one, but in a very way we should understand. But for us to understand it well, I like to show it with diagram. This is the y-axis and this is the x-axis. Now, this is point A, where we have 0 and 0. So this one starts here. And we have another point B. Point B, let here be 2, the xy plane. And then, which place again? At this point, see we have here the point. We also have here another point. Then we have another point which corresponds to 4, the y-axis, that is this particular point. So see how integration is done. See how the triangle is. So we are going to look at this. We are going to integrate along this way. We are going to also integrate along this way. Then later we will integrate along this way. Now all this arrow I'm showing means that we'll go this way, then later we'll go this way. Right. Now, we can take it this way. Along this way, this is B, this is point B. Let me show that. Here is B, and here is point C. So along AB, y equals 0. How? If you recall from coordinate geometry, if I have 2 points like this, and I want to bring out the equation of the 2 points. Okay, now bring it out, the equation of 2 points. If you recall the formula that we used for equation of 2 points, y minus y1 is equal m times x minus x1. So if you do that here, you have the equation of this line, that it is y is equal 0. Now if you have y is equal 0, it means that the y all over the x is equal 0, which also implies that the y equals 0. That is along AB. Now, so we then have that integral over the closed curve along AB become x squared dx plus 1 plus 2x 0, because y is 0, dy is also what, 0. And if you do that, see, provide this is 0, when you times this, everything becomes 0. So what we have is integral of what? X squared dx. And then along that, we can now integrate. The limit of x is from 2. The limit here is from 2 to 0. That is for the x axis. Then we now switch 2 to 0. Of course, if we do this, we will have x cubed over 3. And then we have 2 to 0, which will give us that AB, the line AB now, will now become 2 cubed over 3, which is 8 over 3, along AB. Then, we also go along BC. Along BC, which is this one. So along BC, what happened there? We have that x is equal to, look at it. If you take the line, also take the equation of a line of these 2 points, you have that x is equal to. Now, if x is equal to, it means that the x will be equal to 0. That's what it means. So putting this in the given function, this given function here, we put here the given function. We have that integral over closed curve. Then we have 2, because x is equal to 2 squared. The x, of course, the x is 0, plus 1 plus 2. Then x is also 2, y dy. And this will give us integral of 1 plus 4y. This time this is 4y. dy. You see? dy. And then the limits at that point, look at the limits again. Limit is from 4. Now we are considering this y axis. Limit is from 4 to 0. So we put 4 to 0. If you integrate this, you will have, with respect to y, see, you have y plus 2y squared, because this will be 2 over 2. So 4 divided by 2 is 2y squared. So that we can now put the value of the limit. So we then have 4 plus 2, then 4 squared. And that will give us 4, then 4 squared is 16, times 2. Then times 2 is plus 32. No, sorry, plus 32. The value is 16. times 2. We have 32 plus 4. Then we have what? 36. That is BC, along BC. Now we also look at along AC. That is this one. We want to integrate here along here. Along that side, we have that along AC, y is equal to x. How? Now let's look at the equation of the line. Now we call it for us to look at the equation of the line. Okay, let me do it somewhere here already. Now we see we have 2 points. Look at this point and this point. The equation of the line is given by y minus y1 is equal mx minus x1. And so we want m first. So m is what? M is equal y2 minus y1 over x2 minus x1. You know, m is the gradient. So let's look at the gradient of this line from here to here. If you do that, y2 is this, so which is 4 minus 0, which is y1, over x2 is 2 minus 0. So the gradient is 2. Now, if we come to the equation of the line, we have y minus y1, which is 0, is equal m, here is 2, times x minus x1 is 0. So what do we have? We have y is equal to x. So that is the equation of this line. Now that we have along AC, we have y is equal to x. It means that dy all over x is equal to, which implies that the y will be equal to the x. Now, as usual, we are going to put this into the given equation. We know that from the given equation, we will have that integral over equals of x squared, the x plus 1 plus 2 x, then y, and then y in this context is 2x. So we have 2x dy is 2 dx. So if we do that, it then become integral of the closed curve x squared dx plus 1 plus 4x squared 2 dx, which is the same as x squared dx plus, we have 2 dx plus 8 x squared dx. So this will be the same as, now if we factor out this, we can have x squared plus 2 plus 8 x squared dx. Of course, this is the same as what this and this. We can write 9x squared plus 2 respect to the x integral of this. So we will look at the limits. And the limits from here become 2 to 0, you know, the x side what we are taking. So we have 2 to 0. If you integrate it, you have 9x cubed over 3 plus 2x. Then we have 2 to 0. And if we put 2 here, of course this is 3. So you have 3, you know, this divided 3. 2 cubed plus 2 and 3. Then everything here is, see, 2 raised to the power 3 is 8. 8 times 3 is 24. 24 plus 6, so it becomes 30. That is AC, along AC. Now the closed area now, the total is AB plus BC plus AC. And we do that, we have 8 over 3, the first one. And the second one that we had was 36 for BC. So plus 36 plus 30. That will give us 8 over 3 plus 66. So that is what it will give us. So taking SM of this, we have 3 as the SM, which is 8 plus 66 times 3. You see, 66 times 3 give us 1 198. Yes, 198, which is the same as 198 plus 8 is 206 over 3. Right. So that is the area of, is xy plane. So we talk about the area of that triangle. We have taken it. So now we are going to look at the Green's theorem. That's the Green's theorem.